Okay, so yeah, what we're going to talk about is a very interesting and subtle way in which we can manage concurrent access to shared data structures. If you couldn't tell from the title of the presentation. It happens to be, and I say last time synchronization because this is a lecture from the OS class, and we're going to talk about some of the basic ideas. We're not going to get into all of the gory details, but I kind of mentioned in a previous lecture when I was just sort of telling you, I'm trying to get you to not be afraid of operating systems because they're a really challenging topic, but the biggest challenge is really the concurrency part of it. Everything else is really just a matter of bookkeeping. So you have concurrency, and then you have how do you make it fast and efficient, and the how do you make it fast and efficient really kind of stretches the boundaries on how you manage data structures and so forth. In fact, you probably saw some of that kind of stuff in assignment 5, where you're like, how the hell do I make this tree faster? And so a lot of people did pooled objects and things like that, and that, like we exploit the crap out of that kind of stuff in operating systems because we need it to be as efficient as possible. You know, any data that we use for operating system state management, we're not using for running applications. Any time we use for operating system state updating and so forth, we're not really using for applications. And so we really try to make the OS as efficient as possible. So there's lots of multi-threading issues because of the concurrency, and we already talked about mutexes in assignment 7 when we were just talking about building a very simple mutual exclusion lock. It turns out that there's a lot of other interesting things that you can do in that vein, and we're going to be talking about one of them today. But yeah, there's a lot of shared state. Like I said, this is where the biggest challenge comes from, is in the concurrent access to data structures and so forth. So a lot of this, though, is linked lists. There are a few places where there's more sophisticated data structures that are used, but linked lists are the primary data structure that's used inside the OS kernel to manage various things. So you have the ready queue, which is frequently, well, we talked about multi-level feedback queues, but then you also have things like the Linux scheduler, which is the completely fair scheduler actually manages things as a tree, so it has a slightly more complex situation to manage. File system caches, virtual memory mapping, so we're going to talk about that one today. The number one point, though, the state is almost always being accessed via reads, not writes. It's very infrequent that we actually write to it. If you think about your user space process memory mapping, like assignment 8 was like probably the only time you're ever going to change the memory mapping that much in a single program's execution. That was just like way out there. So in general, though, we have things that are read much more than they're written. So VM area structs, we talked about those and how they describe the user process virtual address space, and you have these nodes describing various details, and we need these to resolve faults. So in our fault handler, we go and look up stuff in this, we read it, and you'll probably notice that in general, our fault handler doesn't need to do any writing to this thing at all. Right? Hey, it's a fault over here. Okay, even if it's private copy on write, I go in and I look at it, and I don't change the VM area struct at all. I change the page table structures, but I don't need to touch VM area struct. So these things are really only manipulated by mmap, munmap, and I suppose mprotect might affect them as well. So those are the kind of the situations where you might modify them. Okay, let's see. Yeah, so trap handler, this is how we get into our operating system kernel. So the obvious question is, how do we actually create a linked list that allows concurrent access, sometimes that concurrent access being a write? Okay. Really obvious solution, anybody want to guess what a really obvious solution would be? Maybe you've implemented this before. A lock, right? We'd probably like, oh, I know how to implement a mutex. I can just put a mutex on the card. Okay. So that's an easy one. We're going to look at a really simple list type. You'll notice we have a couple values in it, just A and B. That's just to make it interesting enough that we might look for certain values of A, and we want to either read or modify the values of B. And obviously we have a node star to the next thing. And so we might have something like this. Okay. Super simple. And so operations might be I need to iterate. You know, you probably saw some of this in the assignment 8 code toward the, when we got to the policy stuff. I want to be able to look for a particular node so that I can look up some piece of information I need. I need to insert a node into the list somewhere. I need to modify a node in the list, and obviously remove a node. Okay, I need to be able to do these kinds of things. And I think we all hopefully know how to implement these kinds of operations by now. If not, then boy, you've made it a long way in CS24. If we try to allow concurrent access to this without any guarding of it, then we have a problem because particularly if we only ever had reads, we'd be fine. But in the situation we start allowing writes, then we start having issues. So like I say here, one thread is traversing the list, searching for A equals 12 so that it can pull out the value of B. So you can see T1, P, that's just thread T1, and its pointer P to the current node that it's looking at. And then you have another thread that's adding a node to the list. Okay. So it's adding a new one with A is 51, B is 24, and it's going to be mutating these pointers. Okay. That's not really a big deal. So far, it's nothing that's really scary. But when you look at how the writer thread is going to manipulate the list, and then you also introduce the fact that the compiler can choose to reorder operations in whatever order it prefers, and the processor now reorders operations in whatever order it prefers. I mean, it does follow some constraints, but we have this sequence of operations. I need to malloc. Now, I am asking you to stretch your imagination a little bit, because if this is inside the kernel, we're not going to be calling malloc. Malloc can lead to page faults, and inside of a kernel thread, a lot of times you can't actually afford to be blocked. And so you have a kernel allocator. Typically, it's exposed via a call like calloc or kmalloc. And typically, you can tell it, I can afford to be blocked or I cannot afford to be blocked. And we'll talk about why you might need to be able to specify that in a little bit. But so we have these steps. A is 51, B is 24, next is going to be the appropriate value, and then you say P arrow next equals new. So you want to manipulate the current node to say it points to the next thing. And the real issue is that we have no idea what order these steps will actually be organized into, because you have a series of writes, right? And you even have the malloc call, and then this manipulation of this thing. So you really can't guarantee, without saying anything, what the order might be. Yeah, question?
Well, there's no guarantee introduced by the fact that the fourth line has a dependency on the fifth line?
Fourth line has a dependency on the fifth line. I think, let me see if I understand what you're saying. P arrow next equals new, new arrow next equals P arrow next. Yeah, so in that situation, you probably have a pretty good guarantee that, well, so really I think the only guarantee that you have is that at the end all of things will be correct. So the end result of the state will reflect that there's a dependency between the fourth and the fifth statements.
But they could have made a temp variable.
Yeah, they could have squirreled away P arrow next somewhere, and they could have been executed out of order. So yeah, I mean, really the only guarantee that you have is that the final state will be correct, which kind of sucks, really, when you know, especially in the context of concurrency. Okay. Yes, but speed, and definitely that's the right way to be thinking about things, is like, but fast, and that's like a really good reason when you're looking at operating system kernels. Okay? And when you look at stuff and you're like, well, here's a design and it's beautifully abstracted and blah, 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 and then you see another one that's gross, but fast, and then you like to choose the but fast one. Okay. So anyway, like I say, you don't have any guarantees. So the way that we reason about this is that this chunk of operations kind of forms a critical section. And so we'd like some way of ensuring that all of these things happen in a way that doesn't screw up other threads that are accessing the same data structure. Now you may also notice another thing about this, and I'm going to sort of jump ahead of the story here a little bit and get your brains thinking about this stuff. But there's really only one step in here that is kind of critical. And if we could sort of ensure that that's the last step that occurs, then everything else is actually pretty okay. The hint is, at what point do all these changes actually become visible to other threads? Yeah, when P arrow next is changed. That's where everything becomes visible to other threads. Now, obviously, if P arrow next equals new was in some way reordered to happen first, then we're like totally hosed, right? Because P arrow next equals new may have happened, and so the new node is there, and new arrow next hasn't been set yet. That would be bad. Or, that's probably the worst situation that you could have here. Okay? Thankfully. This is a really simple case, but you can come up with much more degenerate cases that just make you sad. So in this case, if we can ensure that P arrow next happens after everything else, then we're okay. And they actually there's a kind of operation that you can have called a barrier. Who's heard of a barrier before? Yeah, so it's a term that's used in a couple of different ways. When you talk about concurrency primitives, there's a notion of a barrier that basically all threads have to reach that point before any thread is allowed to proceed past it. So that's a thread barrier. I don't remember if the POSIX threading library has a notion of a barrier, but it's really easy to implement because you just sort of go in and wait. This is a perfect example where, for example, you could use a semaphore and start it out as being a negative number. And then every time you wait on the semaphore, is that right? No, I'm trying to think.
You need to modify it slightly so that
Yeah.
it releases all of them.
Yes.
It is the same.
Yeah, so you can basically build a barrier from other primitives, and so that's a really easy thing to do. Now, on the hardware side of things, you have a couple of kinds of barriers. One is called a compiler optimization barrier, where the compiler, you sort of tell the compiler, you're not allowed to move anything across this line. So anything that happens before the line, you have to finish, and then you can start doing the things after the line. So that becomes an optimization barrier. They turn out to be really easy to implement. And we talked about it in an earlier lecture in the OS class. And then you also have another notion, which is the processor, because the processor can also reorder operations. You have a read barrier, which says all the reads before this point have to be finished before any reads after the point occur. You have write barriers. All the writes have to finish, and then you can start writing other things. And then you have just a plain old everything barrier, which I don't remember exactly what it's called. But it basically, every operation before that point has to be finished before any can be started after that. And I think they're called fences if you look at the IA32 documentation. That there's like an R fence or, I don't know, you'd have to look it up. But basically they're called fences. And they do the same thing. Anyway, so I'm getting ahead of myself. So how do we avoid concurrency bugs? Well, an easy thing to do is to just use a single lock. I already talked about this, briefly introduced this notion. Basically, you have to acquire the lock. Doesn't matter if you're writing or reading, because obviously the writer needs to have some way of guaranteeing that nobody's reading it when it's modifying it. So the writer also has to trust that readers acquire a lock before they try to manipulate the list. So we go ahead and add this lock thing. And, well, here's where we start getting into operating system fun. Okay? There's something special about interrupt handlers. Interrupt handlers are not ever allowed to block. Okay? It's okay for a user process to make a call into the kernel and that user process to be blocked for however long it takes. Interrupt handlers are never allowed to block. They must finish, and they must finish in a bounded amount of time. Because otherwise the entire operating system will grind to a halt. And that's the issue here. So what I'm talking about here, we talk about trap handler, interrupt handlers, and so forth, kernel control paths. Basically, you have a notion of a context. What is the context of this kernel thread that's performing some operation, either on behalf of hardware, because a hardware interrupt occurred, or on behalf of a user application? They executed a read operation. They want to read from the disk, and we know that's going to take forever. So you have the notion of a context, and if you're in interrupt context, the kernel is not allowed to do anything that blocks, which is why calling the kernel allocator is risky, because if you're calling that from an interrupt handler and it needs to trigger a page fault, well, now you have to wait for the fault handler to resolve the page fault, and that's going to take time. So that interrupt handler is not allowed to trigger faults. And you have all these other things that can that you have to make sure that can occur in interrupt context. Yes?
That also means that the interrupt handler can't do anything with virtual memory, right?
Pretty much. I mean, it's allowed to do things as far as, like, change the page table. It's allowed to.
It couldn't read from virtual memory.
It can read from virtual memory if it's guaranteed that it's not going to cause a fault. Yes. And so this is the interesting thing, because again, we're going afield, but hey, this is a special lecture, so we can talk about whatever we want. Some kernels are paged, which means that the kernel is allowed to page out parts of its kernel memory And then, obviously, when you have faults, then you're allowed to page them in. Well, you just have to make sure that certain parts of it are never allowed to be paged out, and you call that pinning the pages, where you can basically guarantee that those pages will never be selected when we're trying to pick a victim. And so that way, you can still access those virtual pages, but you can guarantee that they'll never fault. Okay? And this is also where the whole issue of page faults during page fault handling come into the picture. I mentioned briefly the notion of a double fault, which is you have a fault occurred during a page fault. So I try to call my page fault handler. I'm not allowed to execute it. I get another fault, so that's a double fault. Or I try to execute my page fault handler, and in the process of dispatching, so not that the page fault handler has started, but I try to access it, and the memory that the page fault handler resides in is not in memory, and so I generate a fault. So that's a double fault. And so there's a special double fault handler on IA32, and if that generates a third fault, then you have a triple fault, and that's where the system gives up. That's where the hardware says, you know what, this OS is too screwed up, I quit. And it is not uncommon for students to run into this in the OS class. Okay. Fun. Anyway, so so there's certain things like that. Interrupt context, you're not allowed to block at all. Process context means that you are in the kernel on behalf of a user application, and you're allowed to block as long as you freaking want. Okay? You can take 5 minutes, 2 hours, whatever. Okay. So I believe there's one other context, but I can't remember it right now. But there you have process context and interrupt context are the two most important contexts for why you might be inside the kernel. Okay, so this is just talking about some of this stuff. Trap handler and interrupt handlers, they can disable interrupts. That way you know you can't be interrupted while you're inside the handler. No big deal. So that's how you can ensure that nobody else will interrupt you. On a multi-core system, you have multiple processors running. Well, you can use spin locks. Very efficient mechanism for multi-core systems because you don't have to actually put a thread to sleep and involve the scheduler and all of that. Okay, you can also disable interrupts there. That will only protect you from local threads on that local core, but then you have to use spin locks to coordinate across cores. We talk about that a lot in the OS class, so I won't spend too much time on this. Why must readers also acquire the lock? Already talked about this. The writer needs a guarantee that no reader is actually using the list. So obvious issue. I have a single lock. You could phrase this in many different ways. But all readers and writers must acquire this one shared lock before they're allowed to manipulate the linked list. What's the obvious issue here? Well, in this case, let's assume that this is the only lock we're acquiring. So let's say the deadlock isn't an issue. Yeah, you can't overlap reads, and it seems really obvious that we should be able to allow multiple reads. That would piss me off. I can't remember. I was talking to somebody, and they were like, we had this system, and we changed it from doing just a regular mutex to a read-write lock, and then suddenly the system got way faster. Did one of you guys mention that, or it must have been somebody else? It might have been a TA. Anyway, yeah, so like I say here, we already know, because I said writes are infrequent, that we're going to have a few situations where the writer actually needs to acquire it. So why not allow readers to overlap with each other? Okay. So the way that we describe the problem here is we use this term lock contention, which is basically how much time do threads spend waiting to acquire a lock as opposed to doing useful work. Okay. And you usually measure this as a fraction of the time spent waiting over the total time the thread is allowed. Okay. That's what lock contention is. And so if we have high lock contention, we're sad. And if we have low lock contention, we're like super happy. We're getting a lot of useful work done. Okay. So readers should never block other readers. So how can we achieve this? And I already mentioned that you could use a read-write lock for this kind of thing. Okay. So the premise behind a read-write lock is that multiple readers can acquire the lock at the same time. We allow overlapping read access. And writers have to acquire an exclusive access to the lock. So we have something like this. Read lock and write lock. And then you basically have just one unlock operation that allows you to release the lock. Okay, so this is straightforward again. You can use this. So you get a greatly reduced lock contention. But the problem is that even with a read-write lock, you start, if you're the kind of person that loves to blue sky and think, okay, what would be like a perfect world where I have a pony and my pony has a pony? all that kind of stuff. So you think, well, read-write locks are still expensive, where expensive is measured in terms of probably hundreds of clock cycles. I'd really love to not spend hundreds of clock cycles, even if I'm just a reader, just to acquire this read lock. Okay. And so, again, we talk about this notion of lock overhead. So I already mentioned lock contention. Lock overhead is the other thing that's sort of a bad thing about using locks. Okay. Readers are always incurring this cost, even though we know that most of the time we're just reading. Writers still block everybody, too. So the question is, can we come up with a way to manipulate this linked list that doesn't require writers to have exclusive access? And sadly, the next 10 or 12 slides talk about some interesting alternatives that also use locks. And so we're going to skip that because there's no way we could fit the entire thing into the time that we have. But I'll put the entire lecture up so that you can look at it. The whole idea is typically in these systems you have a dial that you can turn that you may not realize. It's called lock granularity. And basically the lock granularity allows you to shrink the amount of data that is guarded by each lock, and you increase the number of locks. It requires additional complexity in how you access things, because now you have to acquire multiple locks, and so the lock overhead goes up when you increase the granularity of your locking. Decrease. Yeah, increase the granularity means you have finer grain. And so lock overhead goes up, but your contention goes down. So not ideal. So what we're going to talk about, though, is another approach that doesn't actually involve locks. Okay, let's see. Mutual exclusion. So what is the issue that we're trying to prevent? Different threads seeing invalid state. Okay, that's what we're trying to prevent. That's the whole idea behind having these locks. And I pointed out that when we're looking at this thing, if we can ensure that all the other stuff before the P arrow next equals new line has finished before that line occurs, then we actually have a situation where most threads will actually see valid list state. In other words, being able to guarantee the order of these operations is really what we need to be able to do. Okay? And locks are basically just a workaround because you can guard the entire blob of things. So you'll notice that within a critical section that we're guarding with the lock, we don't care what order stuff is implemented in. But what we're saying is all this stuff has to happen, and then we can unlock it, and everything will be okay. Is it a FERPA violation if all you see is that people either have passed or no grades have been entered? I'm trying to think. Probably, yeah. Technically, yes.
Probably is always the answer.
And yeah, I love FERPA. So, and also
Their
names and UIDs I think are up there too. So
that's also a technical less of a problem because everybody has it on their ID card.
Okay.
So that's the sort of thing that if we wanted that information, we would have it already.
Yeah. All right. Well, I'll still have to see what I can do. Fun. Okay. So what if we can impose a more intelligent ordering? This is really sort of the issue here. What we do is we want to do all the steps that involve setting up the node, but not inserting it. Okay? And like I say here, the last three operations can occur in any order. We don't really care because they're not visible. So T1 can go ahead. You can notice that T1 is traversing the list and T2 is mutating it. So T1 can keep going. It doesn't really care. And then the second step is to atomically mutate the list. And like I say, a single word write, so we have P arrow next equals new. It turns out that this operation can be performed in a single instruction on IA32 or x86-64. And if it's D-word aligned or properly aligned, then it will be performed atomically by the hardware, even in the context of multiple cores. So yay, we can do this in a single atomic step. Okay, so notice, before, after, we change the pointer, and now our list has moved from valid state but old to valid state but new.
Only if the new node is still valid, like we were talking about.
Yes. Yeah, so we have to make sure all those other steps occur before we do this pointer change. So really, what we start focusing on is, okay, how do we solve that problem? And like I said, it's pretty easy using barriers. Now, this whole mechanism has a name. It's called read, copy, update. It's been around for actually quite a few years by now. And it uses no locks, which is pretty wild. So read, copy, update basically describes exactly what happens. You basically, when you want to mutate something, you make a copy of it. You make all your changes on the copy, and then you atomically change over to the new version in one instruction. Okay, so like I say here, concurrent readers never see the intermediate state. They either see the old version or the new version. It is not possible to see anything else. Okay, you engineer it that way. Okay, so like I was saying, you make a copy, and then once you've done, you finished making all of your mutations on it, then you go ahead and change over to the new version. So in read, copy, update specifically, all of your state changes turn out to come down to a single pointer being changed. That's always what it ends up being in the system, is that you have some pointer value, you change it from the old value to the new value, and that is your update. And you make a copy, you change it, and then you update the data structure in a single step. Okay, now like I described here, it is useful to think about this in terms of publish subscribe, because basically when you make that atomic change, you are publishing your changes. So you've made some changes in the background. You don't publish something that is incomplete, otherwise people aren't very impressed by you. So you go in and you make all your changes and then you publish them. And then, and like I was describing before, we can use barriers to ensure this kind of thing. Basically, you put a write memory barrier between all these stuff before it and p arrow next equals new. We put a write memory barrier between those two things, and then we can ensure that the previous steps have finished. Like even the processor will not reorder across the write memory barrier. And that's why we need a barrier in that situation. Any questions? Let's publish. So we can do this as a macro. Notice we have RCU assigned pointer, so that's going to be our publish operation. This is a macro, C macro, if you haven't seen these before. So you'll notice that inside the we have to use parentheses around the outside so that we can ensure that it all happens in a single step. And then inside we have curly braces, so we open up a new block and do our things. SMPWMB is a macro that basically does a write memory barrier. And the reason why we call it SMP is because we only need it on SMP systems. We only need it on multiprocessing systems or ones with multiple cores. And then we just say whatever P is, we're going to assign V to it. That's all we really do. So like I say here, and we have a guarantee that this is going to happen atomically already on IA32, so we don't really need to say anything else. We don't need to use any lock prefixes or anything. Just a simple move of here's the new pointer value into the memory location. That happens atomically, even across cores. So this is what T2 does. Notice we have all of our setup stuff. And that can be done in any order, and then we have RCU assigned pointer. So instead of just saying P arrow next equals new, now we just say RCU assigned pointer. And it plops in the write memory barrier, and then we do our thing. Okay? So it really isn't much different. Now T1 needs to be able to see whatever the current state is. So again, we need to think carefully about, well, how do we actually expose the current state? And you'll see here that wherever we look at stuff, so list node start P equals head. We read the current value of head. That needs to be done in a way that plays properly with RCU. P equals P arrow next. We need that to be able to play properly with RCU as well. So anytime we read those things, we're subscribing to the most recent value that was published by whatever writer is written last. Now, the other thing, which you probably say, why the hell do I even have to think about this? P arrow next, that read needs to complete before we access P arrow A or P arrow B. Okay. Well, it turns out that some processors don't guarantee that. The DEC alpha being a notable example. Thankfully, I don't think it's used very widely anymore. Okay. But when I was an undergrad, we had a whole compute cluster of DEC alpha processors. And they had to do this kind of crap because it could reorder stuff. Okay, so basically IA32 has certain rules about what instructions it will reorder. And this is where we can pretty much guarantee that things will happen the right way, because basically if there's a dependency between instructions, the processor will be sure that the final state respects that sequence of, that sequence of dependencies between instructions. So it will reflect that properly, but not every processor does. So thankfully, on IA32, we don't have to do as much work because they tried to design it intelligently. So here's the subscribe operation, RCUD reference. Notice we have this compile time function type of P, which lets us know what is the type of this pointer. So it's just kind of an easy way of writing a function template in C. So RCUD reference, we basically say, I want to access it once. The access once thing basically forces it to not pull from a register. So we force it to read from memory. And then we do SMP read barrier depends, which is like, if on this processor we need a read barrier, put one in. IA32's version of that will be nothing. And then we just go ahead and return whatever the value is. Access once is kind of an interesting macro. I don't think I have a definition of it in here, which is too bad. Oh, I might have one later. But all access once does is it casts P to a volatile. Some of you may be familiar with volatile, but basically it says, somebody else might have changed this. Don't trust it. And then it forces the compiler to emit instructions to read it from memory. Don't trust a cached value in registers. Okay, so access once basically forces that thing to be read. Okay. Everybody got it? So all we're doing is forcing this thing to be loaded from memory. This will basically result in maybe one extra access to memory. Yay, that's pretty fast. Okay. RCUD reference. So instead of having 100-odd clocks or 200-odd clocks for acquiring a read lock, now we're adding maybe 2-3 clocks. So you can see how read copy update is way faster than the corresponding lock-based approach. So here's the updated version of the code, RCUD reference head, RCUD reference pnext. Really, you'll notice that all of the cost of this synchronization mechanism is put on the writers. The readers, we're sort of presuming here that the bulk of our operations, the vast majority of our operations will be reads, not writes. And so, since that's the case, we can try to optimize the read path as much as possible. This is that common case optimization thing again. And we put all the responsibility and all the onus on the writers to take care of things appropriately. The other thing that's really cool is that writers aren't blocking anybody anymore. So we had this other thing that lock contention would spike suddenly when a writer needed to come in and change a data structure. Now we don't have that anymore. The writer comes in and makes a copy in the background. Readers can continue accessing. The writer does all of its setup and stuff. And then we have one atomic change. And so the readers basically never see an issue where the writer wants to step in and do something. The writer really is taking care of a lot of stuff in the background. So it's a pretty amazing approach. It's a really great idea. Okay. Here's another example. We want to now find the node with A equals 19, change B to 15. We're no longer allowed to do this in place. We're no longer allowed to do in-place manipulation. You'll probably also notice that there's a striking similarity between this and functional programming, and it's that would be a good thing to observe. So, like I say, we can't change a node in place. We make a copy of it. We do all of our stuff again. So this is the whole publish. I'm going to set up all my changes, and I'm going to publish them with a single atomic operation, RCU assign pointer. Now remember that this is an atomic operation, and even on multiple cores, it's atomic across all the cores. Which means that we can now use that point in time to divide people who saw the old value of the pointer and people who saw the new value of the pointer. We can sort of divide history at that point in time. Nobody will have seen the change. So everybody either saw the old version or the new version.
So wait, what happens to people that saw the old version?
Well, we need to talk about that. Yeah. And now people who saw the old version, they're just going to keep going down the line.
Well, what if they had the same operation queue?
The same operation queue. Like to modify it?
Yeah.
Yeah, we'll talk about that.
Okay.
We kind of assume that never happens.
Ah.
Yes. And there's a reason. It's a pretty good assumption, in fact. But we are kind of assuming here tacitly that there's only one writer ever at a time. It's a pretty good assumption. Yeah, it's pretty good. The situation, like you can imagine with our VM area structs, the system is probably only going to be calling mmap from one thread, and so those things will be changed. Yeah, cross your fingers and so forth. You could even do something in the kernel like use a mutex to guard mmap calls so that only one guy is writing to it at a time. Yeah. That is a very good question. How do we delete that guy? Yeah, so we'll talk about that because that really is where all the complexity comes from. Okay, so I already sort of pounded that home. Are we finished? So yes, what about deleting? And so what if the writer is just like RCU assign pointer free, whatever the other one was. What is it? Pre? No, it's, well, let's just call it P, right? P is the one that the thread is using. So what if I just say free P? Or thread was blocked, or maybe it wasn't blocked. It didn't have to be blocked. It could just be traversing the list concurrently, and it happened to get the next node before RCU assign pointer completed. So it's in the old version of the node, not the new version of the node, and then we just blew away the node out from under it. We can't really support that. RCU will fail if we allow that. Any problems? If a reader saw the old version, they may still be using the old node when we blow it away. So this is really the bulk of the complexity in read copy update. Because so far it's like, oh, making a copy, no big deal. Changing a pointer atomically turns out to be no big deal, even on multi-core. Thank you, IA32. So the hard part is figuring out when can we actually free the data. And obviously that means that all the readers have to be done reading that thing we want to free before we're allowed to go ahead and free it. So we're going to start introducing new complexities to this to make sure that we can do it. Okay? We have this concept of a read side critical section. And what we're basically saying in the read side critical section is I have to be able to perform all of these operations as a unit. Now, it's not quite as strong as a critical section. So even though we're using the term critical section, it's not exactly the same. What we're basically saying is nobody should be allowed to change the data structure while I'm inside my read side critical section. Okay? That's more or less what we're saying. It's slightly different than that. Okay? So like I say here, the reader enters the read side critical section at the first point where it calls RCUD reference on the data structure, so it starts traversing it. And it leaves it when it's done looking at the data structure. So we introduce a couple of new operations. RCU read lock, hey, I'm entering a read side critical section. RCU read unlock, I'm leaving the read side critical section. Okay? So now we've updated the reader that's traversing this thing looking for the B that goes with a particular value of A. And we use RCUD reference to subscribe to changes. And remember, RCUD reference is really cheap. We like that. And RCU read lock and RCU read unlock to say, here are the bounds of our read side critical section. Okay. So somehow now we need the writer to respect the fact that we have this read side critical section. Okay. You're not allowed to delete this thing if ... We have to figure out the rest. Okay. So here's an interesting constraint on the read side critical section. You're not allowed to block or be interrupted during that read side critical section. So if you're a reader and you've entered, you've done that RCU read lock thing, nobody's allowed to kick you off the processor until you've unlocked RCU read unlock. Okay? So that whole read side critical section is never allowed to be interrupted. That's why we call it a critical section. You have to be allowed to finish it, or basically, or the system can't be guaranteed to be correct. That's basically the constraint here. Now I say here that T1 follows this constraint. Notice it's not making any blocking or possibly blocking system calls. We don't read, we don't malloc, we don't do anything like that inside the read side critical section. But you also have the other concern that this thread can't be preempted from the processor by the kernel inside the read side critical section. So we have to make sure that the kernel respects the fact that this thread is in a read side critical section. Okay? Everybody needs to collaborate to make sure that this works correctly. Okay, so let's start thinking about this. These are a bunch of readers accessing a data structure, and you can see that they access it for different amounts of time. You can think of it basically as the start of the arrow is the point in time where they call RCU read lock, and the end of the arrow is where they call RCU read unlock. So that reader is not allowed to be interrupted for that entire period of time. Now somewhere inside there, we call RCU assign pointer. So the writer was doing some work behind the scenes. Nobody knew about it because it hadn't published it yet. And then it calls RCU assign pointer, and it is an atomic operation. So we know that nobody's arrow starts on that line. It has to start before the line or after the line. And so now we can see some of these readers may have seen the old value. Some of these readers definitely have not seen the old value. Now, do we know that the readers that started before the line definitely saw the change? Because remember, our RCU read lock and RCU read unlock, they're sort of bookend the entire operation on the data structure. You don't sort of like have little tiny bits where they access things. We guard the entire access to the data structure. So it may be, for example, that a reader has started traversing a linked list, it's toward the end of the linked list, and the writer publishes something at the back of the list, or at the front of the list. The reader has already gone past. In which case the reader did, well, I mean, I guess it did see the old version, but it's way past using it by now. It doesn't need it anymore. So it doesn't care if the writer deletes that node. So you can see that the readers that start before RCU's assign pointer may be using the node, but they may also not be using the node. The only real guarantee that we have is that readers that started after RCU assign pointer are definitely, they don't care about that node at all. They don't care if it gets deleted right away. So what we're doing here is we're starting to bound when we're allowed to actually delete this thing. Okay, what readers might see the old version of the data? I already kind of beat that one to death. Anybody who called RCU read lock before RCU assign pointer may have seen the old node. So when can we reclaim the old version of the data? Yeah, so we can look at this and we say, hey, when did all the readers that started before, when do they finish? When the last guy finishes, then we know we can reclaim that data. Okay. Do what?
I said looking at pictures, that's cheating.
Well, yeah, so it turns out that the kernel actually draws pictures, and that's how it figures it out. No, I'm joking. So, but anyway, yeah, so we can use this, though, to reason about it. It's so much nicer to be able to reason about it this way. Okay? So you'll notice that when all those readers have finished, then we can go ahead and reclaim. And like I say, this is the earliest that we're allowed to. We can wait. It doesn't matter if we wait. Really, the only issue that we have with waiting is that we have some resource that is not needed to be allocated anymore that we still have allocated. So it really just means that we need to release that resource. But if we have plenty of resources, it's okay. So this period in between in which we wait for readers to get out of the way, we call that the grace period. Okay? Because if we did not wait the grace period, we would not be showing grace to the readers. We'd be interfering with their lives. Okay? So we actually wait that grace period, and then we can go ahead and reclaim. So all of this complexity in RCU is really about how do we tell what is the extent of that grace period. And so we have a new operation we introduced. You can see we have all these little operations that represent different things. When we get to the end of it, you're going to notice something really unusual, which I really love. So what we do in here is now our writer does this. So we make the copy RCU assign pointer, we publish, and then synchronize RCU basically says, wait until the grace period is definitely over. Now it may wait longer, we don't mind, it just must not wait shorter. Okay? So that's what synchronize RCU does. And then we know all the readers are out of P, and we can go ahead and free it. So yes, all we did was add synchronize RCU to our picture. Okay. How do we tell when the grace period is over? Does anybody want to take any stabs at this? I hope you guys are seeing how all of this stuff draws very directly from CS24 material. That's what I love about this. Like, once you've taken CS24, you have a really awesome foundation for understanding a lot of other things. You actually, it's even simpler than that. It's crazy. It's wild. Readers are not allowed to block or sleep inside of their read side critical section. Okay.
But they can still be interrupted by this.
You're not allowed to interrupt them at all.
Okay.
Yeah, it's like flat, full stop. You're not allowed to interrupt them.
So if you sleep once, then everything should have finished.
You sleep once.
Like, I'm sorry, if you yield once.
Okay, who yields?
The writer.
The writer. It turns out to be a little bit more complicated than that, but you're on the right track. Let's chase this down. What is the upper bound on the number of readers you can have concurrently running at any given time? Yeah, number of cores, right? That's the maximum you can have. So, how can you know that, let's say reader 2, for example, how do you know that reader 2 is definitely finished? Really simple operation. You were actually on the right track when you were saying yield. Context switched.
Oh, because you know when that happens.
Yes, because you're the kernel. It's awesome. Yeah, so if you know that reader 2's core has context switched, you know that reader 2 is finished.
Right, because it's multi-core, you can't wait. You can't just yield once and wait for everything else to happen. You just wait until every single core has yielded at least once.
Yes, that's exactly correct. If you know that every core has performed a context switch, you know that the grace period is over. That's a way to tell.
So you use like a bit mask and then...
I think that's the sophisticated way to do it. Yeah, is that you would have a bit mask and 1 bit per core, and you could just say, hey, every core, I need to know when you're done context switching. So update, just set the bit. And it's kind of one of those, it's kind of like a latch, where you say, hey, all the bits are 0 initially, and then each processor can come in and sort of do an atomic bit set and say, hey, set your corresponding bit. Or you could even do it on like a per word basis, so each core only touches 1 word, and then it's atomic and it's cheap. And so every core has to go in and set their values, and you just wait for all the values to say, hey, I've context switched. And then you can go on. So, but there's an even easier way, which is really wild. Okay, so yeah, I already talked about this. The OS is not allowed to preempt a kernel thread inside a read-side critical section. And which is kind of an interesting thing. We talk a lot about kernel preemption in the OS class, where a trap can be interrupted by a hardware interrupt. That makes sense. Okay, so I'm in the middle of a system call and data becomes available. I want to know about it. So an interrupt can interrupt a trap. That's typical. But you can also have interrupts interrupting other interrupts. That's kernel preemption. Okay, the kernel is allowed to be preempted by itself. So we can actually turn that on and off so that we don't get too wild. Our brains don't have to explode. So we can actually turn off kernel preemption inside read-side critical sections so that even hardware interrupts don't interrupt the reader. So we just turn it off and let the reader finish. Okay.
Is that sort of similar to our scheduler? It's basically like that thread acquiring the scheduler.
Yes, it's exactly like that. The scheduler lock is all about ignoring interrupts while we're inside the scheduler. Because we're on a single core system in assignment 7, whether you have multiple cores or not. And that's kind of the big brain change that everybody needs to realize is that, well, really, even though we have multi-threading, we only have concurrency. We still don't have parallelism. And the only thing that can interrupt anything else in the system is the timer interrupt. And so that lock keeps the timer interrupt from actually getting into the scheduler when we're already inside the scheduler. That's really all the lock does. Okay. But anyway, so we have all this. If the CPU executes a context switch, we already talked about this. So the synchronized RCU, all it has to do is wait for 1 context switch to occur on every processor. Okay? And like I say here, that gives us an upper bound, so that's really all we need. This is how you can implement synchronized RCU. You basically tell the writer to context switch to every processor on the system. Once it's finished doing that, you know that there's been 1 context switch on each processor because you switched to it. Okay? Is this a good way of doing it? Probably not. There's more efficient ways. But it is a way. And that's like what we're showing here is proof of concept that it is feasible. Okay? So yeah, run on basically sets the processor affinity for the kernel thread and then yields. And it will come back on the processor it requests. So eventually it'll get scheduled again, gets a processor, and it says, okay, I know a context switch occurred on that processor. You know that there's clearly better ways of doing this, but this is a very straightforward way of doing it.
Well, just to check, forking requires, if you fork for every CPU, such that you how to fork for each CPU, would that be faster than this, really, or is it?
Well, not a fork per se, but if you the really easy way of doing it is just have some way of telling because every processor has its own scheduling mechanism. They all share scheduler data. But if every core, if that scheduling mechanism has a way of flagging to people, hey, I definitely had a context switch. If you just had some easy way of doing that, of registering and saying, I need to know if you've context switched, then that's all you really need to do. You can do it with timestamps or some kind of thing like that, where you basically say, this is the last time I saw you context switch. Have you context switched after that now? Then you can use simple mechanisms like that. You don't need to create any additional resources or do this crazy thing. It's just slightly more complicated than this. This is just to show you, you can build this whole mechanism. I'll fit the entire RCU implementation on a single page. Okay. So yeah, single processor synchronized RCU is a no-op. Why would that be? Yeah, so we're already inside the writer, and we already reached the synchronized RCU point. We know all the readers that started reading before this point have finished, because we're in the writer now. So yeah, so that's fun. Let's see, so we can go ahead and skip that. So read lock, read unlock, very simple. They turn out to be no-ops as well. Synchronized RCU is doing all the work. On a multi-core system, we do need to be able to disable and re-enable kernel preemption. So we'll go a few more minutes and then we'll be done. So we'll go a tiny bit over. But you can see read lock and read unlock. All we do is we disable kernel preemption and we re-enable it in read unlock. That's all we really have to do. Okay. You can ignore the last bullet until the OS class, where we talk about the way that the Linux kernel manages preemption. Okay. So... yeah, so I'm not going to talk about this just for the sake of time, but read lock and read unlock on a system without kernel preemption become no-ops as well. This is even I don't think that's true on a multi-core system. I'd have to look. Okay, so let me see. Let's just go ahead and go through this. So RCU, unbelievably lightweight. The utilization of RCU in the Linux kernel is skyrocketing. More and more kernel data structures are moving over to using read copy update. For a reason. It makes the kernel faster, especially in these situations where we don't expect very many writers to occur. So like I say here, what you're doing is when you use locks, you're putting a lot of the responsibility for guarding data structures in the lock. With read copy update, you're actually moving a lot of that responsibility to the developer because you're saying you have to declare where your read side critical sections are, and you have to make sure that you copy things before you mutate them. So you're actually putting a lot of that responsibility onto the engineer, which is kind of a funny thing to me. But anyway, yeah, this is the entire RCU implementation. So read lock, if you're on SMP, is preempt disable. Read unlock, preempt enable. RCU dereference, okay, so we have to read that thing once. We need to guarantee that it's read. And like I said, all we really do is cast that P thing to a volatile so that we can force it to be read by the operating system. We emit a read barrier if we're on some screwed up, cockeyed processor that can't do reads in the right order. Okay, and then we just return that. Write memory barrier only needs to issue a memory barrier on multiprocessing systems or multi-core systems, so that can go away on single core. And then we just assign the value. Synchronize RCU, we just hop onto each CPU. That's the entire read copy update implementation. Okay, just to sort of wrap this up, bad and ugly. So there's only certain circumstances you can use it. We expect to have the vast majority of our accesses be reads. Consistency must not be a strong requirement. What do I mean by this? You could never get away with this in a database. And we talk a lot in database systems about transaction processing and transaction isolation. You could never do this in that system because the order of all your operations are extremely important. Operating systems actually don't care so much. And so, like I say here, consistency just doesn't need to be a strong requirement. Okay. Yeah. So let me see. What else do I say here? There's one other thing that I mentioned here, I think, which is that we don't expect there to be multiple writers. There's an operation on IA32 that you may have noticed. It's a compare and swap. Has anybody ever seen compare and swap? Okay. What compare and swap does is it says, if the value I'm writing is this, change it to that. That's all it really is. Okay. And so what you can do in here is, as the writer, you can say, I'm generating my new node and blah, blah, blah. I know what the old value of the pointer is. And I say, if it's still this old value, change it to this new value. That's all I really need to do. And that's atomic, by the way. That's all I need to do to guard against multiple writers. Because if some other writer beat me to it, the old pointer will have changed.
And so at that point, what do you do?
I think you just try again. You say with the new value of the pointer, okay, this was the old value, now I'm going to see if I can change it again. And that way you can guarantee that it's going to be atomic.
But what happens if, like the one instance we were talking about where you try and delete two things, basically?
Yeah.
Because that will fail forever.
Sure. So that's a situation where you'd have to be more careful. It may be in that situation you have to abandon your operation and retry it from the beginning. For example, like if somebody else beat you to it, then now your next value, the next node in the list has changed, so you need to get that and try again. So you might have to go back to the very beginning to retry it. Yeah. So this is, just to wrap up, because I don't want to keep you guys into lunch too long, classic RCU, so very simple. And there's a lot of optimizations that you can use. There's also sleepable RCU, which allows you to actually sleep inside the read side critical sections, okay, which is great. And then preemptible RCU even allows you to preempt readers in the RCU implementation. So this is where we're moving as far as lock-free data structures are concerned. And it's very, very important for operating system implementation by now. Ton of details about read, copy, update. I'll be putting this slide up, or this lecture up, so you can see all this stuff. This guy, Paul McKenney, did all of his PhD research on read, copy, update, and he knows a ton about it. And he's been very happy to share all of his knowledge. And so you have a lot of information out there about it. And then you also have other details about lock-free data structures, which are probably equally important to be familiar with. This is where we get into stuff like compare and swap and so forth, so that you can figure out how to implement those kind of data structures efficiently as well. Again, all of this requires that you have way more readers than writers, and it also requires that you don't have a strong consistency requirement for your implementation. If you have those two things, those two requirements are satisfied, then yay, use read, copy, update, use lock-free data structures, and you'll be a badass. Okay. Any questions? All right, that's it. I'll see you guys next